So our next section is arguably one of the most difficult and without a doubt the longest section we will cover over the course of 2 years in our higher level IB math course. And so we need to revisit a couple topics that we discussed in section 3A that are going to carry over into our new section 3B. And so the first and most important we discussed was the idea of partial sums. And so the idea with an infinite series is if we look at the partial sums, with the first partial sum being the sum of the first term. Obviously, you can't have a sum with one term, but we still think of it that way. The second partial sum is the sum of the first two terms, and the third partial sum is the sum of the first three terms, and so on and so on. And so the idea here to have a series that converges is we want those partial sums to approach some particular value. And whatever they approach, we say that that series converges. And so the question we will throw out there is, how can we tell if these series converge? And so some of the series we've covered up to this point are fairly easy to analyze. Some of them are geometric, some of them are arithmetic, which we don't have to worry about arithmetic series converging because those are essentially just linear functions. But one of the things we need to focus on is, first, again, from section 3A, is the most important idea that if a series is convergent, then we know that the limit of u sub k is equal to 0. And what that basically means is, if we're looking at this particular value of the series, do the values of this approach 0 as k gets infinitely larger? So if you take the first term, and then the second term, and then the third term, and then the fourth term, are those values getting closer and closer and closer to 0? And so we said that if a series is convergent, then we know those values are getting closer to 0. However, if we look at it on the flip side of that, just because these terms get closer to 0 does not necessarily mean that the series itself converges. And one of the prime examples we looked at was the harmonic series, which was the sum from k equals 1 to infinity of 1 over k, which when we plug in our values, we know that's 1 over 1 plus 1 over 2 plus 1 over 3. And we explored this a couple different ways, but we figured out that this particular series approaches infinity. So even though the terms, if you look at them, are getting closer and closer and closer to 0, the series itself does not converge. So again, at minimum, a convergent series has to have terms that approach 0, but that by itself is not enough for your series to converge. And so one of the tests we're going to use, we can say if you have a series where the terms do not approach 0, we immediately know that that series is divergent. And so this idea of convergence versus divergence and using the converse of a statement can get a little confusing. So I decided to come up with a little flow chart here that'll help you guys kind of follow what's going on. And so the first question you should always ask in any series is the limit as k approaches infinity of whatever the rule is here approaching 0? So again, are the terms in the series approaching 0? And so that is what we explored in 3A, and you've really only got two options here. I guess you could always say you've got a third option that is, I don't know, but we're assuming that we're going to have enough tools to either answer the question yes or answer the question no. So what I want to look at first is what happens if you explore this particular series and you find out that the limit as k approaches infinity is not equal to 0. So the limit as k approaches infinity of u sub k does not equal 0. Well, we actually like those. Those are good ones. Because if that's true, then you immediately know that your series is divergent and you stop. There's nothing more to do. But the tricky stuff happens on the left here is what happens if your series does approach 0. Now, we said in the previous slide that if a series is convergent, we know that the limit as k approaches infinity of u sub k is equal to 0, but just having that by itself is not enough to tell if a series converges or not. And so what happens if we answer the question yes? Well, more testing is required. So this, at bare minimum, is what we need. We need the terms to approach 0, but that by itself is not enough. And so what we will explore in the next section is, what do you do? Let me do this here. What do you do if the answer to that question is yes, and you have to apply more tests? Well, that is what section 3B is all about. And we are going to explore all the different tests for convergence. Once you've eliminated this option, so you know the limit as use of k, limit as k approaches infinity of use of k is equal to 0, we now have all these tests. And in the next video, what we're going to do is we're going to explore the first three, which are the easiest ones to deal with. The first is we're going to look at infinite geometric series, which we've been doing now for a year and a half. We're going to look at the divergence test, which is essentially this right here. And then we're going to look at a new one, which we actually explored a little bit when we talked about improper integrals, and we call that the p-series test. And so eventually I will send you guys a link to all the different tests we're going to do. And so these are all the tests that you will be expected to know. And this is a key part of Calc 2. So if any of you end up taking Calc 2 in college, you will almost certainly deal with all of these in some way, shape, or form. And so we have infinite geometric series, we have the divergence test, the p-series test, we have something called the comparison test, the limit comparison test, the integral test, alternating series test, and probably one of the most used ones, which is the ratio test. So at some point you will be responsible for knowing all these, and we will break these into different videos so you can look at each individually and replay the lessons if necessary.